Okay, so while people are trying to join, I will try to take questions from yesterday. If anyone has ideas, questions on asynchronous, and if they tried, what they share your experience, what you have encountered. Has anyone tried to code something with asynchronous call? Does everyone understand what to do, or if you have no idea what went on and you still just know only the name asynchronous but nothing more, you can also type. Great. Did you understand? So Biniam, for example, did you understand how it works?
Yeah, sort of.
And what are the concepts that are clear and that are not clear? So if someone asks you and now you have an interview on a company that is relying on that, what would be something like that you would be comfortable to answer and something that you are not comfortable?
So I used it on a web development project with JavaScript.
Yeah.
So what I understand about synchronous programming is it synchronous or asynchronous? I forgot.
Yeah, synchronous is just more the one you don't use any synchronous call.
Yeah, so when you have two or more processes that can run parallelly, so you can start executing one process and without waiting that process to finish, you can go on to executing the other one. Then when the first process finishes executing, there's a function that's called callback on many languages. So the callback function will be called once the first process finishes executing.
Yeah.
So for example, you can use that to communicate with a server. Yeah, for example, like you don't have to wait.
Yeah.
So like you don't have to wait until the server response. What was it? So you can send a request to a server, and until that response comes back, you can do other things. So, and when the server replies, you can run the callback method and do stuff.
Yeah. So Elakura, just the question is like reviewing if what are the concepts in asynchronous, if someone has used it, and if they use it, what is the part that they are comfortable and what is the part that they are not comfortable. And Binyam was explaining how he used it. And I think this is great, Binyam, but what I would like, just as you move on, like to be more senior, what I want descriptions would be not just, like applied version, which is like, it is useful, definitely, but it's also important to know that you should be writing the JavaScript actually yourself. You should be thinking more like if you're using Python, you should be looking at the Python core codes. If you are using JavaScript, you should be looking at the JavaScript core codes. Don't be happy by just using it, right? It's like the same as what we always, we criticize ourselves a lot more of the time. In Africa, we are users, right? And you should just break that chain now. Have the mentality to like, why am I not writing JavaScript itself? Why am I not writing Python itself? And why, if I have the advantage to use it, why can't I actually at least understand it? you know. So, and the only reason why we become almost always users is because we don't dare to look at down to the core and kind of adopting that mentality. And what I really like, you know, I know this is not easy. I'm not doing it. I'm not there. You know, I'm not. But we are in that together. It is, don't get happy by just using something. It's really the same thing we criticize again and again ourselves. And just, you should be like thinking ahead and saying like, okay, today I'm going to use it, but tomorrow I'm going to look it down and kind of understand what is going on, and such that I can write the next JavaScript, right? I can write the next Python if that is my career. But you know, you don't have to write JavaScript, but you're gonna, like, by that mentality, you're gonna write the next package in data science. It could be the next TensorFlow, right? The next whatever. And only with that mentality we can cross the border. But otherwise, we're gonna be really just always lagging and always gonna be behind. So also when we answer, let's try to be, even if we don't understand it, let's try to be closer to like, okay, what is actually the system going on? Like if I ask how gravity works, there is one way just to say like, oh, it pulls, you know, things down. And another is like, okay, trying to really get closer to just like, okay, why is it pulling? Why is it just actually, you know, things are falling down? Is it the mass? And then you try to answer like, no, it's the mass of the earth is probably bigger. It gets closer, you know, one step level up. And then no, the mass, what does that mass got to do? Okay, Newton's law says that, but is it really like, you know, kind of, and then you get into like, oh no, like it's actually, the mass is really just doing only space curvature, creating a curvature in the space-time, and then that's why, and then the geometry is what. So that is how progress in science, progress in anything comes. And then whenever you look at yourself, I mean, of course, that's if you are an astronomer, right? If you are a cosmologist in that direction. In engineering, it is the same. So what I would really like to say is that try to not be happy for understanding how to use it, and just try to be always searching for one step down. If you understand how to use it, the next thing is like, how does it work? So the same as like, okay, is that the mass? Is that the curvature? Stuff like that with that. So just with, and that's what I'm going to show is just, I think I shared it right now. Just in the talk, in the JavaScript talk, which visualizes Looper. It's also the package, just a JavaScript package. You can just even download it for yourself. It visualizes the internal, the VS code, like the internal, how it works. It visualizes just the compiler using the same JavaScript, right? So you probably have looked at it already. I think is no history. Yeah, okay. So this was the looper that was used in the code in the one of the tutorial that I've used. Like, and this is, you can actually play. So how the loop, like whatever in what the browsers do, like when you write a JavaScript, and when you have, in this case, like, you know, you have one part which if you click it sets this set timeout, and this set timeout is actually just exactly what Biniam was talking. This is what comes from the web API the browser provides. This is just a C++ course, completely different. It's just not part of JavaScript. It's an outside that runs on a different thread. And then this is the main thread that is running on a JavaScript. And so you can see yourself how, and then this is the stack we're talking about. And this is whatever is deferred into the external, basically the browser's external code. That is not just the JavaScript one. And then here is what I was talking about, the queue that is queued. And this is the event loop, which basically takes whenever the stack is empty, if there is anything in the queue, it takes up into the call stack, and then it executes it. So, and then here, just as a simulator, you can actually see that why browsers these days can work so efficiently while you have like a lot of things running, you know, you're requesting some other page and you can go to another new tab. The only reason you're doing that you actually can change tabs is because it's purely based on async, right? Otherwise, you cannot even click anything. If it was synchronous, there is nothing, no functionality or an app, nothing. Basically, once when it's doing something, you'll just be stuck, right? But the reason why we progressed is that because in the asynchronous case, everything basically calls separately, and you can actually navigate while while a page is loading. So you can go and check it. For example, if you do this, then you get here. So this one is set into the call stack, and then yeah, in the meantime, I can do click, and then this becomes in the call queue. So just you can see how the event loop then pushes when the stack is empty, and then it just brings from the call stack until it's finished, right? So, and this process you can visualize while watching also the video. It can help you, and this is the same in Python. So that's why I'm just bringing it here, even if you are not a JavaScript, but this kind of gives you how the actual code internally is working, why it's differing. So it's whatever, like it's put, for example, or rerun, let's say rerun. So the parts that are like logged, console high, whatever that are coming here, while this is not going to run while there is still in the stack something, but once that's finished, then it goes back. So it's kind of, I mean, I'm not explaining it in detail, but because this is not the part that I want to talk today, but this one you can actually play yourself and kind of really understand what this event loop call queues or callbacks that Biniam said in the call stack and the web APIs, but which is in Python would be exactly the same. There will be the main thread, which is basically exactly what is like JavaScript or a single thread. And then there are like C++ codes in Python that are written. So if you use just a normal Python, of course there is no asynchronicity. But if you use some of for example, NumPy is written in C++, therefore, it can run on a separate thread. So while it's running, the event loop in Python controls this one. So it's like it kind of like, if you call an async function, it's basically the same as that async function becomes the web API thing. So it kind of get deferred into that, and then the main thread continues running. And then when that thing finishes, then the callback brings it again to the stack, and that's why you get this kind of parallelism or concurrency. Okay, so that's not the main talk. Now, today's talk is where is the, yeah. So today's talk is on Dask and Spark. So I want to know what people know about Dask or Spark, their experience or parallel computing. So I would like feedback from you where you are in that level and your understanding in parallel computation. So far we talked about multi-threads. That was what I was talking about. And then we also talked about multi-process, which is like if you have independent Pythons running, it could be in the same process, in the same machine, or out, in a separate machine, in a cluster, in a cloud, over the internet, just networked computers. Then you can do multi-processing because they basically have their own separate memory. They manage their own memory, their own threads, and then you communicate between them through a socket. So the socket could be an internal socket, which is the Linux socket normally, or it can be a TCP/IP basically socket, which is basically a port that you're talking. So, but the processes talk completely with a different, message passing. It's called. It's a message passing interface. So, what do you understand by that? And what's your experience? And what just give me feedback. I won't continue without your reflections. So if you want me to go and use the time in more detail, just let me know. Okay, Binyam, he never heard of it. Dask and Spark, PySpark. Anyone else?
Hello.
Go on, Elakura.
I think PySpark is for analyzing big data. I think Spark is for analyzing big data set or something like that. about Spark and all those Hadoop. I'm not really sure, but I think Spark is for analyzing big data sets and all those managing of memory and stuff like that.
Yeah. Okay. So yeah, Wamuyu, it's PySpark is basically just the Spark. Spark is written in JavaScript or the equivalent of Java. Sorry, not JavaScript. And then PySpark is just the Python version. You have RSpark and many others. That just this Anapake project. Okay. Yeah. Anyone else? Okay, for some, Wamuyu, do you want to say something about PySpark? Have you heard or used?
I haven't used it, but I read about it all the time during the competition period. It's for the planning mostly.
Mm-hmm.
Yeah, so I didn't actually get into that.
Okay, so anyone else with parallel computing? So how do you feel about parallel computing? Like, when do you think you will need it? So what is your mindset, for example? Will you be...
Hello, yeah. Is Spark among map reduce? I don't know.
Yeah, it's part. I mean, it's in the same map producer. Hadoop is, it's a parallel computing framework. It's the only difference that it manages its. Yeah, it's in a very similar concept, except that the map producer or Hadoop cluster basically is just a cluster that manages and monitors the different elements in the cluster, which means the different machines, and then it basically assigns, monitors health, whatever. And MapReducer exactly runs on that and does the computation. Yeah, it's type of MapReducer. So anyone have used or took a course on Hadoop MapReducer? What do they understand?
Can I go?
Yeah, yeah.
Yeah, I've not used Hadoop or Spark before, but if it's parallel computing, I understand it's like whenever you have work or a task, you distribute it among the processors of your computer, and they're able to do the work in a faster time. So, for example, in our school, we have access to some class, and we normally submit the calculation. You have to define how many cores you want the calculation to run on. So it's normally the cluster runs it much more faster than our computers because it distributes the work on the cores of the processors from wherever the computer is in. So I think so that's what I know about parallel computing.
Fantastic. Well, that's really good. So what I want is exactly like that. So so if you think of what Google does, what Facebook does, whatever is changing the world. So whatever is changing the world, it doesn't run on a single machine, right? Even from the beginning, the first era, there are mainframes, but immediately afterwards, people understood that they had to, if you really want to change anything, significant work, if you try to model the climate, if you want to run, social things, if you want to get data about users that are if you want to get IoTs that are just generating data per second, if you want to use your mobile, like the apps that are generating data and where they are connected, suddenly it will grow. And to harness data, whether it's called Twitter, Facebook, anything, it just grows quickly. The data you start per day, probably, even if you think of per second, it's sending 1 kilobyte, suddenly you have 3,000, something like 3 times 10 to the 7 kind of per year seconds. And that basically just is, you get in a year a petabyte data. And you cannot store it in one place. There is no one memory that would usually do that. You have to distribute it. And then once it's distributed, it also, the problem becomes you have to actually collect it and put it somewhere. And you cannot, there is no computer that would give you a single RAM that has a petabyte, right? So that means you have to reduce it in some way, in some kind of, by distributing it and computing one step at a time. So you have to develop a new algorithm that does that. So that's what MapReduce is, or that's what many of for example, the pandas or Dask, for example, it gives you like, okay, you have a data that is like huge data. It can be a satellite image that is like, let's say 50 gigabyte. And then you have a RAM that is 4 gigabyte or like 8 gigabyte. You cannot even just load the data. So you start really thinking differently. You're just saying like, okay, I'm going to read part of the pixel. And I'm going to take, if I'm going to like, let's say I'm going to do reducing. So I'm going to take like the resolution, I'm going to reduce the resolution to from, let's say, 100 megapixel to like, to fit it in my memory, I'm going to reduce it to 12 megapixel. And then I'm going to do that reduction while it's still in memory, reading only patch by patch in memory. So from the hard disk, I'm just going to only access. So you need a new type of data format. You probably usually store it because, you know, every data is ultimately zeros and ones. So you order it in such a way, you define where is the 0 point, the coordinate in that one, and then you start like that. That's what all of the, you know, like the processing happens. And so you need a new algorithm, you need a new type of computing. That means you have to basically, the data is stored somewhere in different databases and you have to collect them, you have to call them. And so normally when I was doing, and probably what Gerald was saying, is that usually you have to do that to get fast because this is high-end, huge data. A single second, like not a single second, a microsecond becomes important because you're running the same thing again and again and again and again over a loop. So if you just reduce even a microsecond in one computation, you reduce like one algorithm may take a year, the other algorithm may take you know, a day, right? And that's a huge difference on how you can achieve. And the way you will do those kind of things is kind of like you write your own function using either C++ or using C or Fortran, if it's scientific usually, because those are like low end. That means you don't have overhead in your computation, and you can parallelize. You know, you can manage your own threads, you can manage your own processors. So there is no issue with that. In Python, it is being grown, and that's why you get also very sophisticated tools like Dask and PySpark, which allows you to actually manage with only a small change of your code, you can actually manage your computation in a cloud or in a, you know, in a 1,000 cluster, a cluster which contains thousands of machines. And how do you do that? They have to manage, they basically manage your, like, what are the tasks? So there is a client, and then there is a distributor, and then there is workers. Like in the past, I think we are not going to use anymore, but it's like this slave master approach. So there will be a master like computer that knows where each of, or the kind of the in the high performance computing sense, there will be one node, that the master node, that manages and knows which processor is running what, or which machine is running what, and which data is where. And so they have a database, and then based on that, they allocate, they optimize, okay, to which one to send. Of course, you can also optimize, you know, how data is distributed, how computation is distributed. And these Dask and PySpark are kind of, they really just do that, nothing more. They have a master kind of a node, or like the main node. It's called the name node in a Yarn cluster or in a kind of a Hadoop cluster. And then that kind of the name node contains information about, you know, the health of each of, because they can fail. So the main problem in distributed computing is that suddenly one machine fails, you know, just out of a, you know, for maintenance reason, whatever, and they have to be still stable. And that's why they have to know the health of each of these nodes, these worker nodes, and the worker nodes may have their own trade pools, and therefore they actually also, they manage their own trade pools. But then the kind of the data, which chunk of data they have. And usually also if they fail, you know, you want still other nodes to compute the same data. So you have to distribute it in such a way that there is an overlap. So at least more than one nodes have the same data, the chunk of the data, right? And so they distribute. The name node will basically distribute and keep the database who finished what, at which stage they are, at their health. And then the worker nodes basically takes that thing, compute, and have kind of a protocol with the name node or with the main node on how to send it, whether they should send it, whether they should keep the data in their own processor. So if it is a huge data that you distributed, let's say you have 10 machines and you had 100 gigabyte and you chunk it into 10, let's say, and then you distribute it, and then you basically don't want to collect everything to the name node or to the main node back, because you don't have even memory. So you want the worker nodes to keep, but only you send them a function to apply on that and send it to you. And so the name node basically start only integrating the results, the post process basically. Just they run on that, they return the result, and then you stitch it together and you form hypothesis or whatever computation. That's how big data computation happens. So this is what Dask, this is what PySpark, this is what MapReducer does, right? So I am going to continue with an example, but before that, I want to get questions, because for me, I don't like teaching, because teaching for me is just as a very static process that people, one listens, the other one talks, and then nobody benefits. You know, I know, therefore, why should I talk to you? And you don't know. If you don't really actually apply that knowledge, why should you listen to me? It's kind of a waste. So I think there is no benefit, and I'm a very strong believer in that. If you don't give me feedback and where you are and your status, there's no point for me to continue. So you just have to respond to me with the doubts that you have, with the misunderstandings you have, with the challenge you have that you are not understanding, because I understand it, so it's easier for me. That's why I talk fast. But you probably have no idea, and you may be completely in a different place. So we have to get in the same page before continuing. So is everything clear? And if it's clear, can you now go and code? If not, why? Why not?
Hello.
Yeah. Okay, so there is a question from Miniam first. Are the two alternatives for each other? Yes, so you mean Dask and PySpark, right? They are alternative. Dask is much easier. It's pure Python. So it's it's built just to be a very, very minor tweak replacement for Python. So for example, it has almost every of the functions in many of the functions of pandas. So you have a Dask pandas, or a Dask frame, it's called. So the Dask frame is basically the same as the data frame in pandas, but it's a distributed version of it. And then because of it's a distributed version, you basically can apply exactly what you do, like dot, count, dot head, dot whatever, you can apply on that distributed frame, or Dask frame. So you basically get with minor, without changing any of your knowledge, with even using the same syntax, you basically get a distributed data frame that has been distributed over a cluster. It could be on thousands of clusters, and it manages for you, and it does the computation internally. So yeah, they are kind of alternative. There are of course advantages and disadvantages. One is PySpark is intended for a lot more. It's a lot more used for even to manage on a much bigger cluster, like if you have thousands, while Dask is if you have like 20s, or kind of, it can also work on a single machine. What I'm going to show is in my laptop. So even if you have like one just simple like multi-cores, it actually gets faster because it's designed to be the intermediate one. And then you have Spark, which the same does similar things, but its power becomes much higher because it uses a yarn cluster, and kind of like it becomes more powerful as you get more and more machines. So if you have like thousands of machines, PySpark becomes actually, or Spark becomes really more shiny. Okay, so Ilakuro?
Hello. Okay, I think you were giving an example that, okay, if you have like 15 gig of data and the RAM on our system is 4 gig. So please, can you go over the concept of how PySpark or any of these tools actually distributes the resources? Because we have 4 gig RAM, so how does it really handle the 15 gig RAM? Like, does it make it by batch or?
Exactly. So that's where I am going here, So that's where, just good question to get into that. So normally you have a function, right? And you have a data. The data in this case is X or XY, right? So let's imagine X is a huge array that is 2 gig, right? So you would pass 2 gig data and you get 2 gig data, right? And in a normal, in unparallelized version, that's it. And you can add 2 gigabyte data X, Y is 2 gigabyte, you add them and you get that, right? That's simple. So now the question is, like this X and Y, if they are 100 gigabyte and 100 gigabyte, this is a satellite image. Let's say you want to add, it's a U-band for a very high resolution image of the map of, Addis Ababa, for example. And this one is again, but now with a different frequency channel that is again, 50 gigabyte, let's say, because it's high resolution. It's like, let's say 20 centimeter, like the planet B kind of thing for the whole Addis Ababa, which is basically square, like with a 300, it's 500 square kilometer, but now you have a resolution of 20 centimeter. So you can imagine, just basically it's huge, right? It's basically like in almost like a terabyte. So you cannot load X, you cannot load Y in that case. And let alone the summing, you cannot even do that, right? But normally, if that was simple, you could just do, X is, let's say you get, you increment X and Y and you add Y, and the CPU in this case, just because it's a simple, you get 3 points. So if I run this one, I get this one, that's why. So it's just the time basically runs it for some numbers and I get the time. So it's 3 seconds. The reason it's 3 seconds is that because I added a sleep function here to simulate a bigger data, even if it's just the data is so small, but like that. Now, in parallelizing it, so here is where real happens. You don't load it in the same computer. You load it, just now one is being the data, right? Or X is being the data. So what you're gonna do is that you are gonna, so I'm gonna, yeah. So let's say here, right? So this is reading the CSV. So when you are reading with pandas, read CSV, you're reading everything into data frame DF. Yeah. But now when you are doing it with parallelized one, what you are doing is that you're basically, so in this case, it's just in loop. So it's kind of, I will come to it, but just because they did it exactly that way. So let's say you have chunked yourself before with another processor, you have chunked the data, which was a 10 gigabyte or 100 gigabyte one, into multiple CSVs. Let's say it's a CSV file, multiple CSVs, which are each 1 gigabyte. Okay, so that means 100 gigabyte is chunked into 100 chunks. And let's imagine for now, you did it by hand at some point. You just looped over reading using the Python read, and you read it. And when you arrive to like a certain size, you just dump it into a file. You start a new file like that. And then you have 100 now. You converted 100 gigabyte single file into multiple files. But you want to read them as if they are one, but in a distributed way. That's what it does. So you kind of, then you put them into these file names. You kind of, you get using this, by globe method, you kind of give it like as star.csv because you saved it as whatever underscore 1, underscore 2, underscore 10. So now you can pass just exactly the file names using just this star. You get the file names as a list. And now you get into a loop. This is not a recommended method. It's just only to give you a flow. And then you pass fn, like, so you loop these file names, 100 file names. You read one of it, and then you kind of group whatever. But then the most important part comes, what is by or region? So this is where, like, when you use some people's code, that's the problem. Dask data frames. Let me just go there. So here exactly what we did earlier sequentially. What you did is that you give it to a read CSV, but in this case it's DD. DD is a Dask data frame, right? So in the Dask data frame, when it's initiated, if you just don't pass, so it has basically established the cluster. It lives on a cluster. So if the cluster is now 100 computers, the Dask data frame knows it. So when you read these ones, it distributes each of them to basically the different machines internally. So just by changing PD to DD in this case, because you just loaded Dask data frame, then it distributes the CSVs into multiple machines and it reads them there. Now this DF in this case is not actually really a data frame. If you, I don't have it. That's why I don't think I have the data. For some reason, I don't have the data, but that's why, unfortunately, I couldn't earlier easily get the data. But if I had the data, basically it reads 100 gigabyte data. In this case, not 100 gigabyte because I don't have memory, but in a machine, if you have multiple machines, which has each 4 gigabyte, let's say if you have 100 of those machines, basically they will be, you have kind of an effective RAM of 400 gigabytes, so you can actually handle it. But this thing lives exactly when you read this, it's not reading it.
Hello?
Here. Yeah.
Please, when you talk about we have multiple machines, are you talking about having different computers or same computer?
So it's the same. There is no difference, except the only difference is that in this example I am giving, it's loading each of these files separately in different machines. And you're not going to do the same thing if you have to do for a single machine. For a single machine, you want not the file to be read at all. Okay, so so what you would do in a single machine would be you're gonna really read only a few parts, compute it, and then read another one, compute it from the same. So it's kind of file, when you read file on like when you say, so with open like let's say file dots, in this case let's say it is a big file with TIFF, okay, then so read as F, let's say. And so here when you are reading this one, you're not reading everything in one, right? You're reading from a disk line by line. So that's why you could just go line by line of the code. So what you would do in that case is that you will just basically parallelize this aspect into just like not reading everything in one file, but in one instance, but read only a chunk of it, compute on that, and then save the result, and then compute the other chunk, save the result like that. So if you have a single machine with a RAM, like with a very small RAM, you will not at all read it. You'll basically read only a chunk, compute, and then it's that kind of process. And you can parallelize that if you have like multiple processors, then you can basically then run like, if you have, let's say 4 processors and 4 gigabyte RAM, what you do is that you parallelize with Dask this computation exactly like that, but you're running it like only a chunk less than a gigabyte, and then you pass it to Dask to do it 4 of them at the same time, and then basically you keep like that in a loop. Is that clear, or is that, am I confusing? Because I don't have an exact example for that to show you now because I don't have the data.
Hello, it's clear, but I think the machine you're talking about is the processor, right?
Sorry?
When you talk about maybe having multiple machines, you're talking about the processor, maybe more than one cores.
Yeah. So whenever we are talking machines, we are talking cluster. Usually we are talking different machines. When we are talking cores, we are talking on one single machine. So on this case, mostly like you can assume Dask will work on your single machine. So if I'm reading like that, if there are like 4 files, Dask will know, if it is a single machine, Dask will know that, okay, I need only to read, like to assign, let's say if there are 100 files, so I will divide them by 4. So I will give like 25 to one processor, 25 to another processor, 25 to another processor. but it needs to be ultimately, of course, it has to kind of, it will know also if it doesn't fit, it doesn't read everything. It actually, Dask is smart enough to know that. And therefore it will just then compute. But if it is a huge file, you have to tell Dask how to do it, which is exactly what I was alluding here, on this line, that you have to actually chunk it yourself instead of allowing Dask to chunk, because it may not know how to chunk it. But if it fits, then it can distribute to your processors easily through just basically like assigning, 100, so like 25 of the file into one processor, 25 another. So it does multi-processing for you. And if you have a single only core, it does like basically it can also do it in multi-threading, right? So it knows, depending on the machine it's living, it knows which one to use. So basically in Dask, what you really are doing is that you can read multiple files, or if it's just even a single file, you can specify it. So I'm just going to do this, okay? Where I was I here? Yeah. So now, like let's start import add. And I'll show you examples where I used that myself, right? So if I do that and then help, yeah, so my current NumPy installation is not good. So let me go to Amazon cluster. So here is what I do normally for the, so I log in to SSH. So I mean, this is Amazon now. I'm in the Amazon cloud, and then I can just go where I always work. So, okay. So here, if I do exactly what I was doing, so this is where I use Dask for actual really processing petabytes of data, right? For a company that I'm working. And this is, so if I run just kernel. Okay. Now I will show you a code. So where I use actual Dask for okay, first let me actually see. Here is where to read from S3 bucket. In S3 bucket we have daily streams from our different advertisements that are flowing, how people are interacting, whatever. Okay, and in S3 we have petabytes of that data, but each in JSON, like basically chunked every 15 minutes, there will be one JSON dumped. Everything will be dumped into one JSON every 15 minutes. And I usually need a data that to filter. So there are like per day, it generates usually about 20 gigabyte. And if I want to get a 10 days data, 10 times 20, basically you have like 200 gigabyte of data sitting in Amazon. Not everything I want, I need to filter it. I need to just select those files that I'm interested, and then within those files, because everything is dumped, it's just basically a stream. I want to filter exactly just like a Twitter, right? So I want to filter topics. For Twitter, it will be like topics that are talking about COVID, right? In this case, topics for a single campaign, right? And to do that, I need to call to S3, and then I need to do filtering. But all this is happening via a thread, right? So it's kind of like connection. And I really want to do it over multiple threads, because this connection, as we talked earlier, and I need to do it with async programming. That's exactly where async programming becomes so useful, because I can have like 100 threads because I have the machine that does that. Usually I use 200 threads, and I basically just queue each of those into multiple threads and kind of connect and fetch file, filter it, get data, and like that. So this is the code that I do that, right? So, and how I define threads is basically, I'm just gonna show you here. Okay, so so here is what I do. So in this case, for example, I don't really use even Python's its own kind of like trading. I actually create my own queue, which holds my threads, and then basically it simulates exactly the event loop I was telling you earlier. I kind of have my own stack. I build my own stack. I build my own queue, and I have my own looper, such that I can do exactly that myself, right? So that's why like I build a queue here, and I basically loop over the number of threads I'm specifying. Usually I specify 300 threads, and then in each of those threads, I basically do like, okay, you know, so these are my async classes. So S3 filter thread or S3 list thread. So if one is like a data, then it kind of it filters. Otherwise, it kind of puts it into a list, and then basically the file queue, the event queue, whatever. So I'm gonna not, and then I'm gonna trade the start. So this trading library, exactly, somebody asked me yesterday. I'm using in this case the trading library instead of the async I1. I use exactly, I manage my own threads in this case because I wanted efficiency, right? But the actual async I could even do some, you know, could simplify this thing. But for this particular case, that was not the case. And then the task that I'm using is that, so I get those files. Once they filter, I want to put them, I don't want to put them in my machine, just in the main node that I'm running this code. I want them to distribute, right? So that's where, so I'm reading S3 file. So I'm just gonna, yeah, so get push buzzes, pull, yeah. It's a raw data. So this is where I am doing. So I fetch a raw data from S3, and I basically just distribute it, the data that is there, into with partitions. So, and I partition it into a number of like, because I expect usually 200 gig. So I expect it usually just by the number of files. So like basically this is the data frame size, right? The length divided by kind of, if it is above 500 lines, then I divide it to be in one partition. So basically just this number gives you that if I have a 10 million row in pandas, I will distribute it into basically 10 by that would be 20. So into 20 partitions, so into 20 machines, right? So that's exactly what I do with just only this. DD from pandas, and then split these pandas into n partitions that are like of maximum size of 500,000. And this basically with just this line, I distributed it. And everything else after that I'm doing is I can then do like, okay, you know, group by. I can do group by on this DF data. And that basically is doing in parallel, like in the machines, in the separate machines on each of them. And Dask is clever enough then to know to collect them later when I say reduce, just like a map reduce. If I say like now sum, it knows how to sum using a distributed way. That is the advantage of Dask. So I know this may not be clear, but let me just go back to the question. Yeah.
Sorry, so basically now when you do group by on different data that are splitted in different portions, like how can you sum these things together because they are not in the same machine?
That's what really Dask is about. It does know how to do that. So, and why it does that? I mean, you can even do it yourself manually. And that's basically saying like, okay, you know exactly the index. So you are splitting the data frame by index, right? So you know 1 to 50 is in this machine, 52, whatever is in that machine. Now, if I say group by, what it does is that it sends messages saying like, to each of those machines saying like, do you have, you know, I'm going to start from 1. Let's say I'm taking 1 index where I am grouped by and say like, okay, where are these files located? And then I collect that index and I do the same thing. I'm just only operating on the index and I'm not going to compute anything. And I will save that one as called a state. And then only you will compute it when it's needed. When you need it, of course, you then transfer data from one machine to another using basically TCP, TCP IP, right? So you basically send me this part of the data, send me this part of the data, and that is what the kind of the node or the main node is managing or doing. It kind of manages data flow. And the same is what TensorFlow is doing, you know, basically knows, distributes it, and manages who has what and which data needs to be computed. It's called lazy computation because you don't compute it right there. You only just compute the indexes that are needed for the computation and you save it. And then PySpark is doing the same, TensorFlow is doing the same, Dask is doing the same. So, okay, so where am I? So, what the hell? So, I know this is not a current lecture, and the reason is because I don't expect to do the lecture myself. I expect that you have an interest to know, and I will answer. So, is that clear? If not clear, you can ask what is not clear and how to do it better. Like, what would make it better for you to know? So the first is like I shared with you the tutorial that is really nice, just how to do it. And it's simulated, gives you the data and whatever. So you basically can follow that tutorial and do that. Second is I will just say use Dask. It's a very basic thing on your already existing project, because Dask is really, you don't get, you don't have any issue. Just if you replace pandas with Dask, more or less it's going to be the same. So yeah, so we're going to stop in soon. If you have a question, yeah, go and get out.
What you are showing is like, what's the difference between the parallel programming aspect and the other library I saw a while back called concurrency? I don't know, something like that.
Yep. So like, they're all the same. They're all the same. It's like each of these things gives you a simplification. All of them try to address one thing, that is concurrency and basically, or parallelism with general. All of these things are trying to do parallelism. But you are an engineer. It's like or no, maybe you are not an engineer. Sorry, some of you are engineers, which does basically, the point is that sometimes you want to save money. You don't want to buy a new cluster. You want to use your own computer lab. So let's say you have a computer lab and you want to use it without too much fancy other stacks, computer stacks, like kind of. And in that case, you use Hadoop, because you don't want, Hadoop just runs on any machine. As long as there are machines that are connected with TCP, you can put Hadoop. And the same is exactly, if you have TCP in connection, you can use Dask. So if you want to convert it, if you have already an HPC, a high performance computing, then that's fine. But if you have a computer lab and you want to convert that into a cluster computing machine, then you basically put a Dask into them. So you connect them with a cable. You basically run Dask on that, because Dask only just needs to know that one computer can talk to another using some kind of SSH or some form. Yeah. So
yeah. So like a while back, I tried something, but I didn't have an application for it. So we are like having 2 Raspberry Pis, and then doing a switch and the Intel MPI message passing to connect the two. I could see like the RAM was like to the sum of the 2 RAMs for the Raspberry Pis, the storage. So I think after an academy is something I'll try to run Dask on both of them and see what.
Exactly. Please try it and tell us. I spent most of my life running MPI and OpenMP. Those are the real foundations, right? Like, you know, internally, Python is using some form of that, OpenMP and MPI. So that's called message passing interface, right? So they use message passing interface to communicate between two machines. And they use OpenMP, which is trade, basically the trading library, which does kind of computes on trade. But then to simplify, to allow a lot more machines which have, you know, variety of things to be connected, then you have intermediate softwares, like, you know, you have intermediate products like Hadoop. You have intermediate products like which have their own advantage, PySpark or Spark, which you have Dask. And on top of that, now the current even best kind of that's coming is Kubernetes, right? So Kubernetes is like creating your own cloud. It allows you to do exactly what Amazon Cloud is doing. You want to create the Amazon Cloud in your own clusters, like clusters of machines in your own lab, computer lab, then you use Kubernetes, right? So it's the concept. First, understand the bigger picture. The bigger picture is trying to achieve the same thing. The smaller picture, as you get details, that how can you manage multiple machines with multiple, let's say even brands and whatever. They have even, one has like 2 GB, the other one is 16 GB. How can you put them together, you know, like that? How can you manage, like, because if they are not the same machine, you cannot distribute equally. You know, if you have in your cluster one machine which is very, you know, 4 GB with 2 processors, and another one with like 16 GB and, you know, 8 processors, they can't do the same thing. So you have to be able to really distribute with knowledge, right? So that kind of thing comes with, yeah, like that's why you need Kubernetes, or you need some kind of Hadoop to manage that kind of challenge. While if you have just a simple, you know, similar equivalent machines, you can use just Spark and PySpark. But Spark and Dask, they can also run on top of either Kubernetes or on top of Yarn or on top of Hadoop. So, you know, or on top of any HPC cluster. So is that clear? Does that, Gerald, is that clear?
It's clear. It's clear.
Okay. So I think, yeah, it's like I'll stop here, but I would say you might be confused now. I have no idea if you are confused, if you benefit, because the feedback is quite little, but I hope that you got some advantage. And if you have questions later,
Yes.
whatever, ask. Okay.
Thanks for the session. It was interesting.
Great.
Yeah.
Okay. Awesome, guys. Cheers.
Yeah. Cheers.